Chapter 4, Applications of Differentiation, Section 4.1, Maximum and Minimum Values. Let C be a number in the domain D of a function f. Then f of c is the absolute maximum value, or global maximum value, of f on D if f of c is greater than or equal to f of x for all x in D, and f of c is the absolute minimum or global minimum value of f on D if f of c is less than or equal to f of x for all x in D. These values are called extreme values of f. So what we're saying is that we've got some function floating in a domain somewhere. If this value over here, f of c, is bigger than or equal to f of x for every single other point, f of x, then it's the absolute maximum value. If it's smaller over here, let's say, than every other y value f of x inside of the domain, then it's the absolute minimum value. We say that a number f of c is a local maximum value if f of c is greater than or equal to f of x when x is near c. A local minimum value if f of c is less than or equal to f of x when x is near c. When we say near, we mean on an open interval containing c. These values are called local extreme values. So what we mean here is that it's not necessarily bigger than or equal to every single other f of x, but it is going to be bigger than or equal to all of the nearby ones. So like over here, be bigger than all of these nearby y values. Or over here, it's bigger than all of these, it's smaller than all of these nearby y values. So in that case, it's a local minimum value. But we'll do more examples. Let's see for what values of x does f of x equal cosine x take on its maximum and minimum values. So let's draw cosine. Okay, so it starts at 1, and goes down and up, and same the other way. So roughly that. And it looks like, okay, let's put y. It looks like we have a maximum value over here at 1. So that's the maximum value. The maximum value is repeated over here. And it repeats again over here, and it repeats infinitely often. So over here we have minimum values at -1. Let's see, let's put some x coordinates here. This is pi. This is at 2 pi. So it looks like we have a maximum value at 0 for x at 2 pi. We would have another one at 4 pi, and so on. So for x value, we have maximum values equal to 1 at x values of 2n pi. Basically any multiple of 2 pi for integers n. So for n in the set z of integers. Similarly, we have minimum values of -1 at all of the odd multiples of pi. Because it's at pi, then we'll have another one at 3 pi, we'll have one at -pi, and so on. So to get an odd number, instead of 2n, we do 2n plus 1. That's an arbitrary odd number times pi. Okay, let's find all of the extreme values of f of x equals x squared. Well, we want to know when x squared will be greater than or equal to other values, so it'll be greater than or equal to 0 if f of x is greater than or equal to f of 0, right? Because f of x is x squared, and f of 0 is 0. So that means that f of 0 equals 0, by definition, is our absolute minimum. Because f of x is always going to be bigger than it. This becomes more obvious when you draw the graph, because right over there is definitely our absolute minimum. at 0, no part of the function ever goes below that. So it looks like it does not have an absolute maximum though, because it just keeps going on and on and on. So it only has one extreme value at 0, the absolute minimum. Let's find all the extreme values of f of x equals x cubed. Okay, again, let's draw it. Not so good. Try doing it this way. A little bit better. Okay, so then it looks like it keeps going up forever, and it looks like it keeps going down forever. Over here, you might be tempted to say, okay, well, that might be a local minimum or a local maximum, but even that's not true, because notice to the left, it looks like it's going to be a local maximum, because it's bigger than or equal to all of these points on the left, but then on the right, it's smaller than or equal to all of these points. So it looks like it should be a local minimum. So it's kind of like a hybrid, and that makes it neither. So there are no extreme values for this function. Let's find all of the extreme values of f of x equals 3x to the fourth minus 16x cubed plus 18x squared within the domain from -1 to 4. So we'll use our handy dandy calculator emulator. Let's position it over there. We want to plug in 3x to the fourth minus 16x cubed plus 18x squared. We want our window to be from -1 to 4 for x. So we'll graph it now. Okay, pretty cool. It looks like there's something going on there going down though, and it gets cut off. So let's go back to zoom. And let's go to fit. See if we can fit it. Okay, that looks good. So let's pull that out. Come on. There we go. And we'll put our calculator back. Very helpful. Okay, so now we want to know all of the extreme values. Well, it looks like right over here is bigger than every other value. It also looks like over here is bigger than all of the nearby values. And it looks like over here is smaller than nearby values. And it looks like over here is smaller than all of the values. So we could go back to our calculator, but you could see that this point's going to be -1, 37. This point is 1, 5. Obviously that point is 0, 0. And this point is 3 minus 27. Okay, so we could see that f of 1, which equals 5, is a local maximum. F of -1 is a global maximum at 37. But notice, if we had not cut this thing off at -1, then this would keep going up, and it wouldn't be a maximum. But because we closed this interval, it gets cut off, so this is going to be the highest value. Because the function does not, as far as we're concerned, exist outside of -1 to 4. So this is the absolute max. However, notice, because we cut it off, there are no values left of it that are smaller. In order to be a local maximum, all nearby values must be smaller on the left and right. So that means that this is not a local maximum, it is only an absolute maximum. So now let's look at the other one we mentioned, f of 0, which is 0. That's a local minimum. there. And f of 3 equals minus 27. Notice that it's an absolute minimum because there's nothing smaller in our domain, but all of the nearby points are bigger. It's smaller than all of those nearby points, so that means it's both an absolute minimum and a local minimum. So it is how about I just write it's both a local min and absolute minimum. Our next theorem is the extreme value theorem, which says that if f is continuous on a closed interval ab, then f attains an absolute maximum and an absolute minimum at some numbers inside of that interval. So notice this should make sense just by our previous example. We closed this, which is why we got this maximum value over here. Otherwise, there would not have been any maximum value because this thing would have just kept going up in both directions. Notice over here, this value, it was nothing. It wasn't a maximum or a minimum, even though it got cut off. So in general, though, if we cut off our function, we should expect that cutting it off is going to force it to stop somewhere. So that should force it to have maximum and minimum values. Surprisingly, this is actually pretty hard to prove, even though it makes sense intuitively. So we're not going to prove it, but we are going to use it. The first application should be Fermat's theorem, which says that if f has a local maximum or minimum at c, and if the derivative exists, then the derivative equals 0. Okay. Actually, this is not technically an application. We're going to do some applications soon, but still, this is a very closely related theorem. So suppose f has a local maximum at c. All right, we want to show that if the derivative exists, then the derivative is 0. So first, we know that since there is a local maximum, all of the nearby y values, f of x, are all smaller than that local maximum. So nearby c, we can let h be some positive number that's close by, and that means that f of c plus h is a nearby y value, which means it must be smaller than f of c. Okay, I subtract f of c from both sides. I get that 0 is greater than or equal to f of c plus h minus f of c, and then I just reverse the inequality to put 0 on the right. Now I divide both sides by h because I said let h be positive, so it's not equal to 0. So 0 divided by h just leaves me with 0. And then this thing looks like the derivative if I can just put a limit in front. So I take the limit of both sides. Then I am assuming that the derivative exists. I'm trying to show the derivative is 0. So this value must exist and be equal to the derivative. And then obviously the limit of 0 is 0. Okay, so we've proven that the derivative at the maximum value must be negative, or must be less than or equal to 0. So if we were to, we let h be a positive number. If we were to let h be a negative number, we could repeat the entire argument, but then over here, when we divide by h on the left and the right, this inequality would flip and become a greater than or equal. So that means that in the end, I would end up with greater than or equal to 0. So that means that I would know that f prime of c is less than or equal to 0, and f prime of c is greater than or equal to 0. The only way that f prime of c can be both less than or equal to 0 and greater than or equal to 0 is if f prime of c equals 0. So that proves that if f has a local maximum, the derivative will be 0, assuming the derivative exists. You can use pretty much the same argument to show that if f has a local minimum, then the derivative is also going to be 0 over there, assuming it exists. Okay, so the converse of Fermat's theorem would be that if the derivative is 0, does that force you to have a local maximum or minimum? Which would be super useful. You could just check derivative being 0 all the time, and then you would know for sure. Well, unfortunately, we have this function right over here, f of x equals x cubed, to mess everything up. The derivative of f of x equals x cubed is 3x squared. So that means that f prime of 0 is equal to 0. However, if we look at a graph, let's see if I can draw this again. Okay, so this is y equals x cubed. If I look at 0, I already know that this is not a local maximum min from the previous problem that we did. In fact, what this is it's just a spot where the tangent is 0. So just because you have a tangent that has a slope of 0 does not necessarily mean that you have a max or min. So this means that our converse is false. What Fermat's theorem does tell us is that if we do have a local max or min, then that means that the slope of the tangent must be 0, provided that the slope of the tangent even exists. So another example of where stuff can go wrong is this function f of x equals absolute value of x. Here, if we were to graph it, remember that it looks something like this. Where this sharp point right over there prevents the function from being differentiable at 0. We did an example in section 2.8 where we proved that, well, I don't know about proof, but we showed that the function is definitely not differentiable at 0. So because f prime of 0 does not even exist, Fermat's theorem does not apply. So no. In order for Fermat's theorem to work on any function, you have to have not only a local max or min, but you also have the derivative, just existing in the first place. Otherwise, how could you possibly say the derivative is equal to 0? So in this case, we do have a minimum value at 0, but we do not have a derivative value of 0. So Fermat's theorem works if you've got a nice function where you can differentiate over there, and you've got a nice minimum or maximum, then you know for sure, okay, the derivative exists over there and is equal to 0. I mean, you already knew it existed, but you know it's equal to 0. A critical number of a function f is a number c in the domain of f such that either the derivative at c is 0 or the derivative at c does not exist. So this covers, I think, all of our bases, because either if we had a local max or min, we would have a derivative of 0 if the derivative existed. If the derivative, does not exist, then it does not exist, but, over there. So that's pretty much every possibility for a max or min. Okay, so let's find the critical numbers of x to the 3/5 times 4 minus x. So by Fermat, we say that if we have a local max or min at c, then that means that c is a critical number of f. So if we can find critical numbers in general, then we can test a lot of potential local max or minimums. So let's find critical numbers for this guy, which is going to be good practice for finding local max and minimums. So the derivative is x to the 3/5 times minus 1, we're using the product rule, plus 4 minus x times 3/5 x to the minus 2/5. Instead of the product rule, you could distribute this guy and then just use the power rule. However, I think the product rule is pretty quick, so I'm just going to use it. So this equals negative x to the 3/5 plus 3 times 4 minus x over 5x to the 2/5. Okay, so then that works out to be negative 5x plus 3 times 4 minus x over 5x to the 2/5. And then we just distribute and simplify. We get 12 minus 8x over 5x to the 2/5. Okay, so let's get f prime of 0. If we plug in 0, then we get 12 in the numerator and we get 0 in the denominator. So f prime of 0 is equal to 0 if 12 minus 8x equals 0, which means that x equals 3 over 2, and f prime of x does not exist when x is 0. Because like I said, if you plug in 0, you get 12 on the top and 0 in the denominator, so it wouldn't exist. But if I just want it to be equal to 0, then I just set the entire numerator equal to 0, and I can solve and see that x is 3 over 2. Alright, so those are our critical numbers. Three over 2 and 0. Any number where the derivative is 0 or doesn't exist. Basically anywhere where we have a horizontal tangent or just it blows up. I don't know about blows up. That's not such a good way of referring to it actually, but maybe a corner or whatever. Lots of stuff can happen when derivative is not existing. Let's find the absolute maximum and minimum values of this function. Notice that this function is a polynomial, so it's continuous. Notice that this interval is closed because these are less than or equal signs. So it's continuous in the closed interval from -0.5 to 4. So the extreme value theorem tells us that there will be absolute maximum minimum values of this function. So now we can take the derivative and look for where it equals 0 or doesn't exist. Those are our potential candidates. So we get 3x squared minus 6x. Well, that's 3x times x minus 2. Okay, so derivative is 0. That means that x is 0 or x is 2. And those are our critical numbers. Notice that this function is defined everywhere. It's a polynomial. There's nothing to divide by 0 and mess everything up. So we don't really have to worry about where the derivative is undefined. So let's look at f of 0. Well, if you plug in 0, you get 1. If you plug in 2, you get -3. So at this point, you might be tempted to say, okay, well, our maximum value is 1 and our minimum value is -3. But that's actually not true. Because remember that previous example we did, let's go back to that. When you cut a function off on a closed interval, your maximum value could be where you cut your function off, which is not necessarily going to be where your derivative is 0. Notice over here, this was not a local maximum, so the derivative is not 0 over there, but it's still the absolute maximum. So we must be very careful and check not only places where the tangent line is 0, but also the endpoints. So let's go back. We must check our endpoints to make sure that we're not missing a absolute maximum value. So let's check f of, or minimum value. Let's check f of -0.5. Well, that's 1/8. And let's check f of 4. So we check both endpoints. Well, that's 17. So we would have missed that. It looks like this will be the absolute maximum, because the only place it could be is either at an endpoint or at a point where the derivative is 0 or doesn't exist. It's got to either be at a critical number or at an endpoint. And remember that it has to exist because of the extreme value theorem. Notice also this is our absolute minimum. So in this case, one of our extreme values happened at an endpoint, and the other extreme value happened inside of the interval at one of the critical numbers. Let's use a graphing device to estimate the absolute minimum and maximum values of the function f of x equals x minus 2 sine x from 0 to 2 pi. So we go back to our handy-dandy calculator emulator. This time we're going to plug in x minus 2 sine x, and we want our window to be from 0 to 2 pi. Let's go to zoom first and standardize it. And we'll go to window 0 to 2 pi. Okay, so we want the absolute minimum and maximum values. So let's move over a little bit. Looks like we're getting one over there. Oops. It looks like roughly around 1 is the minimum. And it looks like the y value is like minus, I don't know, between these two, so like minus 0.68. And it looks like our maximum is somewhere around between this and this, so like around 6.97 for the y value, and around like 5.2 or something for the x value. So those are good estimates using our calculator. Let's say that the absolute max, which by the way exists by the extreme value theorem. Notice that this function is a trig function and a polynomial, the difference of two continuous functions, so it's continuous, and this interval is closed, so extreme value theorem guarantees that this absolute max exists. From what we saw, it's approximately 6.97, when x is approximately 5.2. The absolute minimum is approximately, from what we saw, negative 0.68. That's the y value, when x is approximately, let's say, 1. You could get a better approximation if you go over to second calc and hit, how about we do the maximum first, so 4. So we go to the left of the maximum, and then we go to the right, and then we guess it's going to be around over there. And you could see that, yeah, it's around 5.2 and 6.97. If you go back to calc and go to the minimum, then you go to the left of the minimum. Whee! Okay, good. And then to the right. And then we guessed over here. But what we really want to do is use some calculus to find the exact values. So instead of just guessing, even though this is a little bit of a better guess, we're just using this to compare it to what we're actually going to go and calculate. This is like a good check for, actually using calculus to solve a problem. So let's put our calculator back. And let's use calculus to find the exact minimum and maximum values. Okay, so f prime of x. Well, it was 2 minus sine x, so it's going to be, it was x minus 2 sine x. So that's 1 minus 2 cosine x when you take the derivative. Okay, so that means that the derivative is 0 when cosine is a half. Okay, so when is cosine a half? Well, if you look at a unit circle, we want the cosine to be a half. So that's the smaller x value. So that's over there. And it's also a half over there. So that's at pi over 3, or if you go all the way around, at 5 pi over 3. Remember, we're cutting this off from 0 to 2 pi. It's on a closed interval. Okay, so those are our critical numbers, because this thing's not going to be undefined anywhere. So now let's look for to evaluate the function at those critical numbers. Well, f of pi over 3 is pi over 3 minus 2 times the sine of pi over 3. So that's pi over 3 minus radical 3. Because the sine over here, if cosine is a half, then sine is rad 3 over 2. And then 2 times rad 3 over 2 just becomes rad 3. Okay, so that's about negative 0.68483 if you use a calculator. Let's do f of 5 pi over 3 now. So that's the same thing, 5 pi over 3 minus 2 times the sine of 5 pi over 3. So that's, 5 pi over 3. But in this case, sine is negative over there. So that means that this is minus a negative, so it's plus rad 3. Alright, so that's about 6.968039 if you use a calculator. Remember, we also have to check our endpoints. Our maximum or minimum value is guaranteed to exist by the extreme value theorem, but it's not guaranteed to exist when the derivative is 0. It could be at one of the endpoints of our closed interval. So it could be at 0, and it could also be at 2 pi. So at 2 pi, this thing equals 2 pi, which is about 6.28. Okay, so looking at this, I see that this is the biggest y value that we got. Remember, if our maximum and minimum exists, which it does by the extreme value theorem, it has to be either at a critical number or the endpoint, so it has to be one of these 4 values, because this is all of our critical numbers in the interval and all of our endpoints. So that means it must be here for the maximum. And for our minimum, it must be here. So it looks like in this case, yeah, you could say, okay, you didn't even have to check your endpoints. It wasn't over there, but you always need to check your endpoints because it could have been. You didn't know. So let's write that our absolute minimum is at pi over 3, so it's f of pi over 3. And the exact value of that, without rounding, is pi over 3 minus rad 3. Our absolute minimum is f of 5 pi over 3, which is 5 pi over 3 plus rad 3. Notice this is consistent with the graph we got in the calculator. Our minimum and maximum values were not at the endpoints, and they were approximately equal to these values. So the calculator can be really good to check your work after, but notice that it couldn't give you this exact value without a computer algebra system. The Hubble Space Telescope was deployed on April 24th, 1990 by the Space Shuttle Discovery. A model for the velocity of the shuttle during this mission from liftoff at t equals 0 until the solid rocket boosters were jettisoned at t equals 126 seconds is given by this function v of t in feet per second. Using this model, let's estimate the absolute maximum and minimum values of the acceleration of the shuttle between liftoff and the jettisoning of the boosters. So I underline that because they gave us velocity and not acceleration, so we have to take the derivative in order to do this problem. So acceleration will be the derivative of velocity. So that's the derivative of 0.001302 t cubed minus 0.09029 t squared plus 23.61t minus 3.083. Okay, so then use the power rule. We get 3906 times t squared minus 0.18058t plus 23.61. So it looks like if you don't like decimals, you definitely should not go work for NASA. Alright, let's take our derivative. Remember, we need to find critical numbers, and we need to find endpoints for our interval, which looks like it's from 0 to 126. And then we need to check all of those for the maximum minimum value. Okay, so a prime of t is equal to 0.007812t. So we had to do the derivative twice, because we needed to take the derivative just to get the acceleration, and then we had to do the derivative just to check for critical numbers. So we actually had to get derivative of acceleration, which remember is jerk, but doesn't really matter. Alright, let's look for where it's equal to 0. So it equals 0. Solving for t, we get that t is 0.18058 over 0.007812, which is about 23.12. Okay, so a of 0 is equal to 23.61. That's our first endpoint we have to check. We have to check our second possibility is our critical number, which is a of this thing. You should plug it in before rounding though. So how about I call this t1? You have to plug in a of t1, and you get that that's approximately equal to 21.52. Then you check your last possibility is your other endpoint, 126. You see that that's about equal to 62.87. Okay, so it looks like we have our maximum over here, and at 126 at one of the endpoints, and it looks like we have our minimum inside of the interval. So it was important to check all three, especially since we only had one critical number, but the extreme value theorem guarantees us that we would have a maximum and a minimum, so there would have to be one at an endpoint. So we can write that the maximum acceleration is about 62.87 feet per second squared, and the minimum acceleration is about 21.52 feet per second squared.